our fall 2019 Capstone presentations. I just wanted to share a little bit of information about the course and why we're here, and some of the people who are involved in NRES as a whole, as well as the Capstone course here this fall semester. So right now, and I just pulled these statistics this morning, we've got here at Kansas State 95 students that are actively pursuing the secondary major in natural resources and environmental sciences. That is a high number for us and represents a big comeback in terms of comparable numbers that we saw in this program in the mid-1990s. So it's a real encouraging sign that we're seeing more enthusiasm, more excitement about the secondary major. To me, in the context of our secondary major, the thing that is most exciting is that our students come from 6 different colleges and 32 different majors. So as you'll see here in a second, I think this population of students really helps us achieve some of our major programmatic goals within NRES. Here this fall, we have 6 majors from 3 different colleges represented, a total of 13 students. And sneaking a peek at next spring semester, again, we've got about 8 majors and 4 colleges, nearly 20 students. One of our biggest capstone courses, at least in recent memory, here in the spring. I won't go into a lot of detail here with this slide, but these are our official NRES student learning outcomes. And rather than maybe read each of those bullet points, I took the liberty of highlighting some key terms. And I'd like you to notice how many times things like broad perspective and multidisciplinary or interdisciplinary approaches appear. And that really is our goal with NRES, is to build upon the depth of knowledge and skills that you've gained during your time here at K-State within your major field of study and get you involved in a practical, real undergraduate research experience which affords you the opportunity of working with people who maybe think about natural resource or environmental topics, at least in a slightly different way than you do, or that you're accustomed to seeing these topics presented. That is our goal with NRES as an interdisciplinary overlay to a major. We're going to hear from a number of groups, 3 different groups here in a moment, but I also wanted to share as well that one commonality between all the research presentations that you'll see is the study area is Marion County Lake and Park. If you don't know where Marion County Lake and Park is, I should have brought my laser pointer. Just to the right of the .com there in the label, you'll see Manhattan, and then I've got my Google Earth bubble highlighting the location of Marion County Lake and Park. Here's a close-up. We're not talking about the large Corps of Engineers reservoir, Marion Lake, but the smaller county-owned lake and park, which is highlighted here as well. This will be the 4th semester that the NRES Capstone course has tackled projects with this common study area, which is, to me, also an exciting aspect of the class because we have real clients and they are very interested in the results from these projects with the long-term goal of developing a lake management plan for that county resource. Before I get the first team up here to get us started, I do want to make sure I thank on behalf not only of myself but the NRES Governing Board our key points of contact at Marion County Lake and Park. Matt Meyerhoff, a K-State and NRES alumnus who approached us with this idea of working at Marion County and has been key in our efforts over the past several semesters, as well as Lisa Suderman, who runs the Watershed Restoration and Protection Strategies effort for Marion County, Isaac Hett, who's the superintendent at the Lake and Park, and Ricky Robert, who's the Marion County representative from K-State Research and Extension. I also want to recognize and thank very much our faculty mentors this semester. For the students, it's important to know that there is very little incentive for faculty members to come in and share some of their time and expertise during the semester. It really is kind of a volunteer effort. I'd like to thank Tricia Moore from the Department of Biological and Agricultural Engineering. Thank you, Tricia. Greg Newmark from Landscape Architecture, Regional and Community Planning, and Arno Temme from Geography and Geospatial Sciences. So thank you to all the faculty members. Last but not least, Carol Seven, our Academic Services Librarian, has been super helpful in several aspects of the course, especially our library class and library tutorials. So without further ado, let's go ahead and get started. Do we have an order in terms of who's going first? Do we have a volunteer?
Ready? Okay, well, good morning. Thanks for coming today. My name is Krista Long.
I'm Caitlin Vicker.
I'm Emily Bauer.
I am Brooke Hogan.
And I'm Daniel Stitch. And we will be presenting on our project about the phosphorus content in soil surrounding the Marion County Lake. And so here's the kind of roadmap of what we're going to be talking about: the site description, the methodology, then the results of our testing, and then the discussion of what you kind of need to take away from this, and then the conclusion. And then to start out this, what kind of drove our project was these research questions. And so we started out with these four, or generalize them into these four. They are: how do the soils observed around the lake compare to the soil map of the area? How much phosphorus in the soil surrounding Marion County Lake? What relationships exist between soil characteristics and measured soil phosphorus concentrations? And do the observed soil properties lend more to phosphorus losses in the lake or phosphorus retention?
So Dr. Hutchinson touched on some of the basics about the site description. Here we have the map of the lake again, and the most important things about it is the lake is 153 acres of water surface area, and the watershed that drains into it is about 4,000 acres. And those 4,000 acres consist of both residential and agricultural land use. And probably the other most important thing is that the soil unit that's surrounding the lake is the climb-sown soil complex, and so it's a mixture of the climb and sown soils, and it's a silty clay loam, and all of the areas surrounding the lake where we took our samples were from that particular soil unit. And yeah.
Okay, so next we're going to talk about our methods. So we took some soil samples out at the lake. You can see all the samples that we took are these little red dots. Hopefully you can see them. So we used a combined judgment convenience method of sampling. So the judgment is basically we picked points that we thought would be significant, would have significant results, and then we made a pattern of 4 samples at each point. So you can see the first one was right as close as we could get to the shore, and then we did 12 yards out and out and out. So mostly our notes were descriptions of the profile, redox features, and any effervescence. We tested for that in the field. And then we sent them to the K-State Soil Lab to have them test for phosphorus. And again, like Daniel said, all the points were in the climb-sloan complex, and slopes ranged from 2 to 17%. Slide. Sorry. And so our testing is we used the Melick test from the soil lab. That's the test that samples for the amount of phosphorus in the sample. It's good for basic and clay soils, which is what we have. And then we did an ANOVA test. It's a statistical probability test, and we get the p-value, which is the likelihood that data is from the same population. And then we also did a standard deviation on the data as well when we got it back, and that's just a measure of variance.
Okay, so the results from our soil testing. So we tested for a lot of different parameters, and as mentioned earlier, we had 16 different samples. And so parameters that were tested for in the lab include organic matter, pH, we looked at soil texture, we looked at phosphorus, we looked at organic matter, CEC, and then some other different nutrients. And so significant parameters for us were the soil texture. And so you can see here on the textural triangle, we have all 16 samples plotted. So they're arranged by color. So the colors of the dots correspond to the transect that they were from. So you can see they're all silty clay loam, and then we have some that are silt loam as well. And then another really important thing for us was to look at the soil phosphorus. And so that was kind of the main focus of our research. And so it was interesting. We had one transect B, that had really high phosphorus, which you see in blue there on the screen. And so that transect was actually really close to the stream that feeds the lake, and it was also really close to residences. So we thought that was an interesting observation, some factors that maybe contribute to that high phosphorus concentration. But then you see that the rest of the transects had pretty uniform phosphorus concentrations. Yeah, that's all I have for that.
Going backwards. There we go. So this slide here summarizes the values for the properties that we measured versus expected values according to the soil map. So we generated a web soil survey report, which is a service produced by the NRES that has a list of values for, or range of values for CEC, general expected soil texture, pH, sodium absorption ratio, all kinds of things. And we pulled the values from the web soil survey report relevant to our research. So the expected cation exchange capacity for the limestone soil complex surrounding the lake is 22.1 milliequivalents per 100 grams of soil. Organic matter is 3%, and texture is salty clay. You can see that our cation exchange capacity is some much higher, some a little bit higher, but they're all higher across the board. Same thing with organic matter, and our textures were a little bit coarser than we would expect. They had a little less clay and more sand and silt in them, especially the silt loam one, transect A. This slide here summarizes some potential correlations between the phosphorus measured in the samples and other soil properties. The p-value is an indication of how likely or unlikely a soil property relates to its phosphorus concentration. A high p-value means that there's not a strong relationship or causation between them, and a low p-value is vice versa. A low p-value would mean that it's very likely that those two things are related. So distance from the shore, not a big factor here, it looks like. Slope and organic matter and distance to residential areas seem to have a much stronger relationship to soil phosphorus. And then we have a graph here with phosphorus versus cation exchange capacity. So in soil, phosphorus tends to attach to iron and aluminum oxides and act as a cation. So soils with high cation exchange capacity are able to hold on to their ions more strongly than soils with low cation exchange capacity. So it's interesting to see that soils with high CEC have high phosphorus concentrations, so that might indicate that high CEC soils are holding on to their phosphorus really well out there around Marion County Lake. We also did a calculation to see the phosphorus stored in the soils around the lake. Most of these are conversion factors, just there's 0.45 kilograms of soil in a pound of soil and such like. The underlying value over there is from our data. And so what we did was a conversion for each sample point to see how many kilograms of phosphorus that would put in the entire mapping unit if that one point was a representative sample for the whole map unit. So we did that for all 16 points and then averaged it. And then multiplied that by, and to get like kilograms of, or we got like multiplied by the acreage. But anyways, it comes out to about 1,300 kilograms of phosphorus surrounding the lake. And then we used the K factor from the Web Soil Survey report, which is an indicator of how much soil is lost per acre annually via wind and water erosion. The underlying value up there is the K factor from the Web Soil Survey report. I can't remember exactly what it ranges from, but we don't have a terribly high K factor, meaning that we don't lose a ton of soil, but perhaps a more moderate amount of soil annually via wind and water erosion. The other underlying value, the 12 milligrams of phosphorus, is the average concentration of phosphorus per sample across all 16 samples. And it comes out that it looks like we're losing 0.309 kilograms of phosphorus annually. One thing that's interesting about, or important to note about that fact, is that's just phosphorus lost by attached to the soil. So it doesn't really account for dissolved phosphorus in groundwater and that sort of thing.
So to conclude our presentation, we kind of just wanted to answer those questions. So if you kind of got lost in the information, we can answer those for you. So for the first question of how do the soils observed around the lake compare to the soil maps in the area, like we said, the soils we found were coarser than expected with higher CEC and organic matter. And then for the second question, how much phosphorus in the soil surrounding how much phosphorus is in the soil surrounding Marion County Lake, and we said it was 1,300 kilograms. And then the third question was what relationships exist between soil characteristics and measured soil phosphorus concentrations. We found out that the phosphorus content appears to be related to the slope and organic matter, but not, sorry. Yeah.
It's not related to distance from the shoreline, but it is related to slope and organic matter.
Yes. And then the last question, do the observed soil properties lend more to the phosphorus losses to the lake or to phosphorus retention? And we said that soils are holding on to the phosphorus well, but more testing needs to be done to make this conclusive.
The reason that we say more testing needs to be done to make it conclusive, if you remember, transect B had much higher phosphorus, so we feel that that transect could be an outlier, and maybe the rest of the soil has relatively low phosphorus concentrations. All the calculations that I discussed in the discussion section of the presentation gives an equal weight to each measured value. So the really high phosphorus concentration counts just as much towards the average as the really low concentrations, even though we have more measured low concentrations than high concentrations. So. Are there any questions? Are we doing that now? Yes.
Why is it important to know phosphorus content in soil?
So phosphorus content in soil, it's important to be careful with how much phosphorus is entering water generally. Although phosphorus isn't super mobile in soil, if you have a lot of soil phosphorus and a lot of erosion going to Marion County Lake, it could really contribute to the phosphorus concentration in the lake, leading to water quality impairment issues. Any other questions? Yes.
So for that one outlier point, you mentioned that it was kind of by like residential and in the incoming, where the water incomes to the lake. Have you considered how much the water from or the phosphorus from runoff contributes to the phosphorus in the soil at all? Like does it?
From the surrounding area or?
Yeah. Mm-hmm. Like potentially from housing, et cetera.
Yeah, so we were thinking that potentially is a factor of why that phosphorus is really high, but honestly with just one data set, we can't really make that conclusion, so that more testing probably needs to be done, in areas that are, more areas around the lake that are close to residences to really conclude that that is a relationship.
I saw on the map that you put up where your points came from. How did you choose those points specifically? Because it looked like there wasn't really anything at the southernmost part.
One of the defining characteristics that separate the Klein and
Hey, can we pass that mic around?
Oh,
sorry. One of the defining characteristics that separate the sown and the climb different soil types is the slope. So we selected our sites based on, we had 2 that had a steeper slope and 2 that had a shallower slope, so that we could get a good analysis of the entire soil unit.
Something like season or rainfall, because we had a lot of rainfall this past year, would that affect results?
So the reason why one of the things we looked at was distance from the lake shore was because since we had so much flooding and then recession of water, we wanted to see if maybe areas that were more frequently flooded from the lake would have higher phosphorus versus ones farther away. And it didn't seem to be a huge issue, but that doesn't really answer the question about like runoff from the surrounding area, which Chris had talked about.
Statistical analysis, what was the direction of the correlation with the slope? I don't remember. Was it positively correlated with slope or negatively?
So we found that less steep slopes had higher less steep slopes had higher phosphorus content, which would make sense if water is sitting, more on a less steep slope.
Just distance, the elevation as well. Might be.
All right, let's thank this group one more time. Nice job.